Okay, now I'm on take 3 of this video, but hopefully this is the one. And so let's get to it. It's 1.5. So let's go. Here we go. We can do it. So the informal definition of a limit, or the intuitive definition of a limit, they say that f of x is defined. So you have some function defined at x near some number c. I'm going to show you a picture too. That means it could that f is defined on some open interval that contains c, except possibly at c itself. So that means that it could be it needs to be defined in the neighborhood around c, but may or may not be defined at c. Could be defined, may not be defined. Then they say the limit of f of x as x approaches c is equal to L. And that's the notation for that. If we can make the values of f of x arbitrarily close to L, so the output's very close to L, as close to L as we like, so you could say within 0.1 of L or within 0.0001 of L. So they say arbitrarily close, which means I can choose that, but I need to choose it by restricting x to be sufficiently close, so I can calculate how close x needs to be to meet that condition on either side of c, but not equal to c. So this is the picture, and so this is a little, the picture, I think pictures kind of show things really well. So what it's saying is, as I approach c from either side, the output is approaching L from both sides. And so the function's output is very close to L from both sides when the function's input is very close to C. And that doesn't matter if it's defined at C or undefined at C. So now that I filled that in, it's defined at C. And still the answer for the limit would be still L. And when it's not filled in, it's undefined at C. I don't know if I'm going to be able to erase that very well. And it's still, the limit is equal to L. There are 3 ways to find a limit from a table of values, and we're going to check those out in 1.4, which was the last video. We actually looked at table of values, and also in 1.5. We're also going to look at from a graph in 1.5, so those are what we're doing now. So reviewing tables and looking at graphs as well, and then algebraically using the limit laws in 1.6. So, and that'll be next, right? So here, it says, guess the value of the limit if it exists by evaluating the function at the given numbers, correct to 6 decimal places. To compare, I expanded problem 20. So I did do a little more than problem 20 asked in the book, if you're a person that likes to look in your book. And they asked you to use the table method to find the limit as x approaches 1. And so of this function here. So for this function, and I want to show you what I calculated here. So I'm saying let x be 0.6, and then we're going to find the output. So when x equals 0.6, then we're going to look for the output then, and the output is our function right here. So it's what squared minus 3 times the what divided by the what squared minus 9. And what we're putting in here is 0.6. I wonder why it's having trouble with its focusing a little bit. Hope it's not my camera saying it's done, right? And so don't get so melodramatic, right? So here I'm going to be putting in 0.6 squared minus 3 times parenthesis 0.6, and then downstairs parentheses 0.6 squared, and then minus 9. And so it'll do it. It's 1/6. And now I could, with this same screen, I could go and I could change that to 0.7, to 0.8, the 0.6s, 0.99, 0.999, and that's how these values were got. You can go check them if you like and make sure that I have them all right. I hope I do. And so anyway, so for 0.6 we got 1/6, which is, when I write it as a decimal, I'm going to put this on its side, 0.16666, and then 7, right? If I round appropriately to 6 decimal places. So they're wanting me now to look at, and they're saying they don't even want me to know what's happening at 1. And so is it defined at 1 or is it undefined at 1? And actually it's defined at 1. I could plug in 1 here and I would get a value. And so what does it look like as you get closer to 1? What does that output look like it's getting closer to you? So from both directions, it's getting closer. What do you guys think? Yeah, I think I agree with you. I think I hear you all the way from the future and from, it's getting closer to 1/4, right? Which is also 0.25, right? So either one of these is good. This is what I would put, but either one of those is okay. So it actually, this was actually defined, our function is actually defined at 1, okay? And so now they're wanting us to talk about what if it's not defined. So at 3, it's actually not defined, our function here. And so they're asking me to find the limit as x approaches 3. So we're going to get closer to 3 from both sides. And they asked me to evaluate all of these, and I'm not making you do all of them just because I thought, oh, that just takes so much time. But I just want to show you what we're doing, and then you could go find them all when x is 2.6. And our function is what squared minus 3 times the what over the what squared minus 9. In the case, it's the same, right, as what we had. So I'm going to be able to come in here, was it 2.6? Oh, that's so convenient. And I'm going to be able to put a 2 in here and edit this to be 2.6. So 177 over 56, it asked me to write it as a, so S to D. And so this is 3.16071 6 places, and the next number was a 2, so I would, rounding appropriately for, I'm trying to make sure there's not other things that it's trying to focus on. And so now they're asking me, they're saying guess or make a conjecture of the limit, but they're asking me to look at based on the evidence that I got. So as I get closer to 3 from both sides, as my x's get closer to 3, a little bit smaller than 3 and a little bit bigger than 3, but getting closer to 3. And I'm not looking at what's going to happen at 3 itself, because actually if I plugged in 3 itself here, it'd be undefined. What does it look like the outputs are getting closer to? I agree with you, half. Okay, so we did good finding the limit from a table. One more, finding the limit from a table. So now they're asking me as x goes to -3, and this is a place in the graph where we actually have an asymptote, and so we're gonna check out what that looks like. So it's a place that's undefined, and it turns out to be an asymptote. So I'm kind of looking at, this one was what they say it was, they said that it was a hole in the graph. So it was a place that's undefined and a hole in the graph. So when you get undefined, when you're plugging in, you can either have a hole or an asymptote, and we're going to learn to figure out which one it is. And so that's going to be our story. So I'm going to be putting in -3.5, so x equals -3.5. So that's when I'm going to be testing into this, right, what squared minus 3 times the what over the what squared minus 9. And fortunately I still have that on my calculator screen. Oh, did I mess up there? It looks like I did, and I didn't get in 2 on that other one. Let's make sure that I didn't make a boo-boo. I'm not shooting it again because I'm already on too many takes on this video. Darn it. Darn it. I think I failed to put in the 2.6 and I didn't even look at it. And I hope that some of you were screaming at your TV, at whatever you're watching this on. So that's 3, the 5 is 6. Yeah, that makes a little more sense with the pattern there, right? It was at least bigger so than it was. And when you, of course, what was I really looking at to find the limit as I got closer, right? This was actually too far away for me to even look at, so I didn't even really notice the pattern of marching in there. Okay, but now I feel better that I fixed it. And so now I'm going to put in negative 3.5. Here's where if you didn't use parentheses, you would actually get the wrong answer. And so if you failed to use the parentheses, you would get the wrong answer if you did it. And so I see that with calculus students all the time. If I had a nickel for every single time that a person in calculus or in above calculus made a math error because of lack of parentheses, I'd be a millionaire and I would just be laying on a desert island right now. Deserted island. I don't know if I would want to be on a desert island. 7, so that's what I'm getting there. So exactly 7 here falls kind of in the pattern. And so now you can see that as I grow closer to negative 3 from a little bit smaller than negative 3 and a little bit bigger than negative 3, that my numbers on the coming from the left are they're 7, 31, 61. It's not honing in on something like it did. It looks like it's getting bigger and bigger. And on this side, these are negative. So it's getting negative but bigger, which is really actually smaller, right? When it's negative, bigger numbers as you go. And so this side looks like it might be going to infinity, where this side looks like it might be going to negative infinity. If you weren't for certain, I mean, it certainly looks like that, you could pick something even closer to negative 3 from either side and see that it's even bigger. So my guess, since the two sides are not the same, what I'm going to say is the limit does not exist. D-N-E, does not exist. There's that famous scene, right, in Mean Girls. So to sum up what we found, we said the limit as we went to 1 was equal to a quarter, and so as I get closer to 1, here's 1 right here, and this is actually a solid dot there, and it's getting closer and closer to a quarter. Here's 1 up here, and you can kind of see, oh yeah, so from either side. This right here should have been a hole in the graph. So when I come over here to 3, I'm going to put a hole in the graph. One of my students actually told me how I could go and put a hole in the graph, and I forgot to do it from last semester from Desmos. I didn't know how to do it, but now I do. So there's actually a hole in the graph there. But you can see that from either side, from the left and from the right, the limit is half, just remembering back, right? And then here at negative 3, so this is negative 1, negative 2, negative 3, we found that on one side, here's this asymptote I'm going to go put in here, that on one side from the left, we said it was going to positive infinity. So as I get closer to negative 3 from the left, it's going to positive infinity. And as I get closer to negative 3 from the right, it's going to negative infinity. So we said this does not exist. Okay, so put that little hole in your graph over there. And so just to see what we found on the graph. So this was kind of linking, because remember they were going to do the table method and the graph method in this section. So I was trying to kind of link what we found to the graph here. So that, okay, so I want you to look at what I've got going here, finding the limit, finding the value of a limit from the table of values, guess the value of the limit if it exists by evaluating the function given to correct six decimal places. So I want you to put in here that, just so that we can practice putting it in. So trying to find the limit as x approaches 0, and you can see that as I'm going here and I'm getting closer to 0, right? So that's my goal there. And so as I approach 0 from a little bit smaller than 0, and remember your calculator needs to be in radians, and now I've picked up a different calculator here than I used the last time I showed you that it needs to be in radians, but that's a little r, so it is in radians right now. And you would do the same thing, shift setup to put it in radians. I use Casio's. If you like to use Texas Instrument, then that's fine as well. I'm okay with that. My son told me that he had an interview with Texas Instrument, which was bad news to me in more than one way. Bad news because I didn't want him to live in Texas, wanted him to live in California so I could get to see him because I really like him. And but the other bad news was that I think Texas Instrument calculators are like too far gone. I don't really think that he could fix them. He's a real smart guy and all that, but I think that there's just so few things wrong with a Casio that if he got a job there with a Casio, he could really help. So I got this value here. If you're like, could you have put that in using the fraction key? And the answer is, yeah, I sure could have, and I don't know why I didn't, because sometimes I'm talking, chewing gum, and thinking about food all at the same time, something along those lines, whatever my problem is. So I certainly could have put it in just like I saw it, and I would get the same answer. So if I'm looking from this side, it appears, right, if you were going to make a good guess, that it looks like it's approaching 1. You can even pick another value if you like. And so would you guys agree from the other side, it looks like it's approaching 1. And so we might guess, right? It was our conjecture from what we have. And most of the time what people do when they find a limit using the table method is they don't use a lot of values. And so I use 3 values on this side and 3 values on that side, but sometimes people will just use 1 value and say, well, this one here. And that's where you have to be careful, because if you guessed at it, 1 seems reasonable from what we have here, but it's not right. It's wrong. So that's the reason the table method isn't a good method of finding a limit. You can be tricked. You can be fooled. And so I want to show you what the graph looks like of this. So this is y equals cosine of 1 over x, and it actually over here so that's why the table method is a pitfall, leads to pitfalls. I'm just looking at a little bit bigger than 0. The other side would look exactly the same. It's their cosine is, what's that called again? Yeah, you got it, even function. Cosine is an even function, and it's alternating wildly. So that if you chose a value here that's even closer, like negative, and maybe I'll do 4 zeros, and then maybe I'll do a 1. I don't know. And I put that in. So I'm going to go put in a couple more zeros here. So I got 4 zeros and then a 1. If I tried that, here you notice I got negative. That doesn't go with the pattern, right? Negative, and I just chose another value. So I just kind of got 3, 6, whatever it is. So this looked like it had a pattern, but now I see that if I even get closer, the pattern is broken. And over here the same way, you could choose some other value here that's closer to 0. Maybe I'll choose 5 zeros and no negative, and maybe a 2. And so let's do that. So I'm going to come in here and do another 0, and I'm going to change that to a 2. And I'm going to take out the negative. And here I get negative 9, it's negative as well, 9.8, coincidentally, negative. I didn't know what it would be. Could have been anything. It could have even turned out to be half. And so I just know that it would be a number between -1 and 1, right? Because that's where cosine goes, between -1 and 1. And so it actually could have been anything. And so And if you pick something else, And so I'll challenge you, pick a few more, and you're going to see that getting closer and closer to 0 from both sides, and you're going to just see that the pattern was here, but now that you're picking some values here, the pattern fails. And so it's not getting closer to 1. And it's because it's oscillating wildly, is what they call that in your book, oscillating wildly. And so really the answer should have been does not exist. So D and E does not exist. So here they talk about some notation for the left-hand limit and the right-hand limit. So when we look at when it's coming from the left and when it's coming from the right. So they put a little, it's not an exponent, but it's in the position the exponent would be. Is that called a superscript? I don't think it's called a subscript of a negative. And that says X is approaching A from the little bit smaller than, from a little bit smaller than A, from the left-hand side. And they call that the left-hand limit. And it's like coming from the negatives are on the left and the positives are on the right, I think, how it goes. And approaching A from a little bit bigger than A, approaching A from a little bit smaller than A. And then this is approaching from both sides. When you just go to from A, you have to consider the left and the right. And then this is a theorem out of your book that if you're trying to find the limit as X approaches A, then it exists if and only if the left limit and the right limit exist and are equal to the same value. And so this is equal to L. So it exists and is equal to L only if the left and the right are both exist and equal to L. So we're going to try here. This is problem 6 out of your book, and they just ask a ton. They give this graph. Here they have the oscillating wildly there at near 5. I don't know why the Stewart book, he doesn't label the graph all the way up. Sometimes when I get a graph off Desmos, it's not labeled all the way up. And I kind of find that I just kind of want to start labeling it. It helps me. Anyway, so there I filled in, and I'm going to label this here 2, 2, 3. It shouldn't drive me crazy that it's unlabeled. What should drive me crazy is that I forgot to get myself some tea. But okay, so this must be called H. Yeah, the function H. And they want me to find the limit as X approaches -3 from a little bit smaller than -3. So here's -3, and I want to stay a little bit smaller than -3. And I'm making myself into like an ordered pair machine. So if X is -3.1, then the output is nearly, 3.9. If X is -3.01, then the output looks like it's around 3.99. If X is -3.000001, then the output is nearly 4, right? And as I continue saying what X is, and my X's are getting closer to -3, and I'm checking what is the output, I'm saying more and more, nearly 4. So that's the answer, 4, right? Because that's what it's approaching. It's getting nearly to 4 every single time, getting closer and closer. Now, from the other side, -3 from a little bit bigger than -3, I want to stay on this side, which is like -2.9, right? Where am I at? Well, maybe I'm at 3.8 there. And a little bit closer, where am I at? Oh, well, I'm getting a little closer to 4. A little closer, so as my input becomes a little closer to -3, but stays bigger than -3 and doesn't get exactly equal to -3. So I don't know if there's a hole in the graph there or not. I'm not allowing myself to get there. My output is nearly 4. So this is also equal to 4. And in order to find this, I would have to look at both. I'd have to look at the limit as X goes to -3 from a little bit smaller than, which was 4, and I'd have to look at the limit as X goes to -3 from a little bit bigger, and it's equal to 4. And because these are the same and they both exist, then this is equal to 4. this would be in my thoughts. And so if someone asked me to justify my answer, this is what I would be telling them. Well, the left limit is 4, and the right limit is 4. So that must mean that the limit is at 4. Now I want us to look at what h at -3 is. So this was saying get really close to -3, but always stay smaller than -3. But get really close. Really, really, really close, but never get there. This is saying get really, 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 really close, but stay bigger than it, right? This is saying look at both sides being really, really close. This is saying don't look at what happens on the left. Don't look at what happens on the right. Look at only at -3. Look at exactly -3. And so when I look at exactly -3, I notice it's open. And so that is undefined. Now, just to be clear, had the graph looked like this, not good drawing, and maybe too small, right? So all of the stories that I have going wrong here. So flipping my paper over. Hi, Ty, I'm in studio. Can I call you back? Okay, bye. So that's my son, Tyler. He'll either snip that out of the video or you'll forgive me. One of the two. I'm not sure which one. I hope you'll forgive me anyway. Okay. Let's say that you had this. And let's say, so I've just drawn that picture, that they asked you to find h at -3. Do you know what the answer would be? Yeah, it'd be 5. Because I don't look at what's happening to the left or what's happening to the right. Now, if I asked you to find the limit as x approaches -3 from the left, it would still be 4. And from the right, under this picture right here, it doesn't matter what's happening at exactly -3, it would still be 4. So the limit as from both sides would still be 4. So it doesn't matter what is happening when you're finding the limit exactly at -3. And so we would get the same answer. Anyway, I just wanted to make that clear. I hope that that's not one of the problems up here ahead of time, and then I just made a new example that was just like example I already had. That can sometimes happen to me. I get so excited. I just love math. I can't help it. So this is the limit as x goes to 0 from a little bit smaller than 0. So I want to stay on this side of 0. So I'm looking at if I'm a little bit smaller than 0, what's the output? And if I'm a little bit smaller than 0, what's the output? And it looks like I'm getting closer and closer. As my x's get closer to 0, what do my outputs, my y's, get closer to? That's what this is saying, right? But stay smaller than 0. Looks like 1. And what about if you stay bigger than 0? So here I am, and my x's are going to get closer to 0, and I'm looking, what are the outputs? The ordered pair, right? So the x value is very close to 0. The y value is very close to, yeah, -1. And it doesn't matter if this had been open or closed. Now, to be a function, one of them would have to be open and the other closed because of the way it's, the way that they're at 0. It is, right? And so otherwise it wouldn't be a function. But it wouldn't have mattered. The answer would have still been -1 had that been solid. Just like this would have still been, the answer would have been 1 had that been open. And now I'm looking at 0 itself, but you know, noting from E and F, what we found in E doesn't equal what we found in F. That means this does not exist. And then h at 0, just because the limit doesn't exist doesn't mean that h at 0 is undefined. H at 0, well, h at 0 actually is equal to 1. Exactly at 0, not really close to 0. So now we're looking at 2. And it says both sides. So I notice that as I come from smaller than 2 and work up there, it looks like from the smaller side it's approaching 2, and from the bigger side it's approaching 2. So from both sides, so from the left, it's going to 2, right? And the right, so this is what I'm thinking, it's also going to 2, so that means from both sides it's going to 2. So in my thoughts, I want you to, I'm writing, make sure that you know that I thought about both sides, the right and the left. Well, what about at 2 itself? Well, at 2 itself, it's undefined. And then the limit as we go to 5 from a little bit smaller than 5. So on the little bit smaller than 5 side, it's where it's also oscillating wildly. So that does not exist. And from a little bit bigger than 5, so this other side, it looks like if I stay a little bit bigger than 5, right, and I look at what's the output, a little bit bigger than 5, what's the output, but getting closer to 5, it looks like the output is very close to 3. Okay, so they asked me ones from a graph, and we're going to be looking in class at some pretty tricky ones from a graph for the fun of it. This graph came out of your book, and they didn't put the asymptotes in here, so I'd like to put the asymptotes in here. Okay, so there I put the asymptotes in, and I guess this is the function a. And they're looking at the limit as x goes to -3, so I need to look from both sides. So when I look from the left, a little bit smaller than -3, looks like it's going to infinity. And you could put a plus in front of it if you want. So writing infinity or positive infinity is the same. And from the right, well, a little bit, it looks like it's going also to positive infinity, right? And so from both sides, it's going to positive infinity. Now the limit doesn't exist because infinity doesn't exist, but it usually says, and it doesn't in here, but if it does not exist, then you would specify if it's going to infinity, positive or negative infinity. And so in this case, it is positive infinity. I've seen some high school kids, because I think they do this on the AP test, write D and E, comma, positive infinity. And that's good too. To me, when you say that it's positive infinity, this is implied that it doesn't exist. And so, but I'm good with you writing that, of course. I mean, it doesn't bother me. Now, not every time that something does not exist, is it going to infinity, positive infinity, or negative infinity. So like oscillating wildly, it wasn't going to positive infinity or negative infinity. It was truly just does not exist. Some people say that my does not exist, my D makes it look like it says 1, but it's D and E there. Okay, so I try not to, but you know how it goes. So I'm going to 2 from both sides. So when I look from the left, a little bit smaller than 2, it's going to negative infinity. So as I march down here, negative infinity. And from the right, it's going to positive infinity. These are not the same, so this would just be does not exist. And I hate to put equals on that. So, and they don't in your book. They're pretty secretive about it. They put equals like if it was 2, equals 2. But they just put in the back of the book positive infinity or does not exist. Now I'm at a little bit, oh, wait. Careful, careful, careful. it only asked from a little bit smaller than. Pardon me. I tried to answer the question like it was this one, but it says a little bit smaller than that. So this is negative infinity, right? And this one a little bit bigger than, we just answered that question, positive infinity, right? And so from both sides is does not exist. And I don't know why. I sometimes write capital N, and sometimes I write lowercase n, and sometimes I write capital E, and sometimes I write lowercase e, and I don't know what my problem is that I can't just be consistent on that. But I don't, to me it's not a difference. And so I didn't label where -1 was, so I want to label that here on the graph. So here's where the y-axis is. So here is where -1 is. And it asked from both sides on -1, and I noticed on both sides it was negative infinity. And then it asked the equations of the vertical asymptotes. So there were 3 vertical asymptotes here, 1, 2, 3, and it asked you to say the equations of them. And so this one here, the equation of a vertical line, is x equals, and your book says a, and I always say a number. And so, and maybe not, maybe your book doesn't even say a, maybe it's my algebra book that says a, and I say x equals a number. So the equation of a line always has x and y, or x only, or y only in it. It has something. And so I often get as the answer -3. And then when I mark that wrong, people go ballistic on me, and they say something like, my high school teacher said that was okay, or whatever have you. No matter who you say said that was okay, give me your name, give me their name, and I will call them. Some people have actually given me the person's name, and I have called them, and they said, I never said that was okay, because that is not a vertical line. And so x equals is what you need. X equals -3. So that's the first vertical asymptote. The next one is at x equals -1. And the third one is at x equals 2. So there, this graph had 3 vertical asymptotes. So there they all are. And there you have that. Okay, so that's 1.5, hot diggity dog, and we'll call it a wrap.